Assalamu alaikum. Welcome to lecture 26 of natural language processing. So in the last lecture, we had talked about the transformer. So transformer is a neural network model for processing sequential information. And at the end of the last lecture, we also talked about BERT, which is a neural network model based on the transformer. And BERT was basically proposed as a language modeling approach and as a approach for learning a model that is pre-trained. So once you have a pre-trained model, you can fine-tune it for another task that is related to that. For example, you can take a pre-trained BERT model and use it for, let's say, sentiment classification or for topic classification or for any other NLP task. So we talked about transfer learning as well last time, and we said that there are two main types of transfer learning. One is, you can say, fixed, in which you learn something before the current task, like word embeddings, and then use those word embeddings in the current task. In the second case, you learn an entire model on a related task, and then you adopt that model on the current task. Of course, for the current task, you should have some data as well to adopt the model from the pre-trained model that was trained on some other data set. So transfer learning, as I mentioned, has kind of revolutionized NLP, and we have now very good performances on many classical tasks in NLP as a result of transfer learning. So today, I will talk about BERT briefly, and then we'll move on to discussing machine translation. And we will discuss the models that are used for machine translation, and then we'll also talk about an evaluation measure for machine translation. So that is the agenda for today. So are there any questions? So let's briefly talk about BERT. BERT, as I mentioned last time, stands for bi-directional encoder representation from transformers. So this is a architecture that was developed to learn language or learn a language model. And of course, it is also used for transfer learning, because once you have learned the language model, instead of learning only the vectors for each words in a language, you can reuse the entire network that has been pre-trained on that language. So retraining and fine-tuning is also possible. Also, to distinguish this type of, you can say, embeddings from the ones that we have studied already, like word-to-vec, this is sometimes also called contextual embeddings. So why is it called contextual embeddings? Because you get a representation for a word based on the context in which that words appear, in which that particular word appears. So previously, when you learned word-to-vec, for example, for any given word, you will have just one embedding based on whatever training data set that you had used. But now for using word-to-vec, once you have trained the word-to-vec model on some data set, when you're applying that model, you are giving a new sentence to it. So that new sentence with all the words in it would also generate embeddings. So those embeddings would then be contextual embeddings because they are based on the new sentence or new running text that you have given to the model. So these, as such, are called contextual embeddings as opposed to the fixed embeddings that we had previously from word to vec. So basically, we talked about the transformer last time. So transformer has an attention mechanism, which is, you can say, an attention layer, you can call it. After that, there might be some fully connected layers or feed-forward layers, and then you might have an output layer. But most transformers would have multiple such sets. So this one set, one attention layer, one feed-forward and output is called a block. And they could be multi-headed, multi-heads, or you can call this a head also. So there are usually multiple heads in a typical practical transformer. So the BERT that was proposed originally, it was, by the way, BERT was a work from Google, Google AI, and it was proposed in the 2017, 2018. So it's relatively new. And so the original models, they proposed two models. One was the base model, which was a smaller one, and the other was the large model. So the base model, had 12 encoders. So when I say 12 encoders, these are in series, one after the other. They are stacked, one after the other. Okay. But each of those encoders also has 12 heads or blocks. So these blocks, of course, are in parallel. We talked about this last time as well. So each block is processed separately and in parallel. And each block would cater to maybe some different semantic or syntax or information relating to the words in that sequence. Okay? And the assumption is that if you have multiple blocks, each block would cater to something different, and at the end you concatenate all that information to create one output, and that one output is then fed through the feed-forward layer and the output layer. So, and of course, now you have 12 encoders. Within each encoder, you have 12 heads, and of course, after the first encoder, the output of the first encoder goes into the second goes into the third goes into fourth, until you go to the last. So as such, you can assume, of course, each multi-attention head has multiple parameters. We talked about WQ, WK, WV, and then of course you have parameters for the feed-forward or fully connected layers and so on. So the total number of parameters for this model is over 100 million. So lots of parameters. So this was their base model. The large model has double this capacity. So you have 24 encoders, and each encoder has 24 heads. And then the number of parameters in this model is over 300. So these are complex models, large models. And as I said before, these were developed for language modeling. But since this is a transformer, it is not an autoregressive language model. It's, as the name suggests, bidirectional, but as we will see, it's not truly bidirectional. You might call it unidirectional or unidirectional language model. So they use a different way of modeling language. So let's look at that. So what they propose, actually two tasks, and they use both of these tasks together to train the model. The first task was the Mast language modeling, and we'll talk about this shortly. And the task 2 was the next sentence prediction. So let's talk about this. So what is the Mast language model? So previously we were talking about the traditional language modeling, where we wanted to predict the next word given the previous word. So for example, I give this, I live in Lahore, for example. So whenever I'm at position live, I have seen I and I've seen live, and I want to predict the next word, which hopefully should be in. Okay. So this was our traditional autoregressive language model, and we discussed the transformer using this application. Okay, last time. Of course, you can combine two transformers and make them bidirectional. So you can start from the right side, you can start from the left side, and then combine the output for the position live, and then generate the output. But that has a problem because especially for language modeling, for some other tasks, it might be okay. For example, for POS tagging, it might be okay, because POS tag is a tag set different from the word vocabulary, while the word vocabulary is what you are actually predicting in a language model. So if you are seeing the words after the model as well as before the model, then you actually know what is the next word. So there is nothing to learn then. So that is why, if you recall, when we talked about a traditional transformer last time, we did masking. We kind of zeroed out the information from the next following word. Otherwise, the model would learn it directly without any adaptation. So to ensure bidirectionality, or to ensure information from the next side and the left and the right side, they came up with a interesting idea. So let's say I have that sentence, I live, and I kind of mask the word in Lahore. So now this is my sequence. So the word in is masked, and we'll discuss how they mask it. Mask means that it's hidden. And this is the word that we actually want to predict. Okay. So of course, this is fed into a transformer. Okay. So transformer means that all this information goes in at once. And for the masked word, we predict at the output layer over the entire vocabulary the best word for it. So the output for the masked, let's say masked word is A3, right? Third position pair. So of course, this goes through some feed forward, some output, and you get Y3. Okay. So Y3 is a distribution over the vocabulary, and you will get a probability, and based on that probability, you want to get the word that is most likely at this position. But whenever, since this is a transformer, A3 would be able to see all things. I live as well as Lahore. Okay. So we have seen everything there. So the idea here is that, of course, again, the same problem would arise if we do it for all the words without any other modification. That the neural network automatically kind of learn this from other examples where we have not masked this. We have masked something. For example, we have masked live, and we have not masked I in. So it will learn it from there. So इसमें तो कुछ randomness डालने की जरूरत है if you want it to learn it properly. So what they did was, so whatever corpus that you have, so you mask only 15% of the words randomly. Okay? So only 15% of whatever corpus that you have, 15% of the words from the corpus that you have are masked, and these are chosen randomly. And of those masked words that are chosen or selected, we further do this thing. So 80% of them are, you can say, masked, meaning that mask means that you give it some random vector, not the vector of that particular word. Okay? Random vector, or maybe you can even set it to zeros. So the 10% of them are set equal to some other random word. So this is the variation that is introduced. So some other random word, कोई और random word का vector यहाँ उठा के डाल दिया आपने, ठीक है? And then the remaining left 10% of them is set to the actual word. So जहाँ जो actual in word था ना वो भी हमने इसको दिया, but of course उसकी probability कम है. And then of course we train this over a huge corpus. We train it of course multiple times. And the idea is that ये जो mass word है, position है, इसकी output हम ले रहे हैं, बाकियों की नहीं ले रहे हैं हम. So the mass position है जो A3 in this case, we are only getting the output for Y3, Y1, Y2, and Y4 ki, we are not concerned about that. And of course, these Y3 is about one of the 15 that is selected, 15% that is selected from our corpus. Okay? So, so given this, you train the network. Of course, this is one of the tasks. So let me mention the other task. The other task was, task 2 was next sentence prediction. So next sentence prediction, of course, is you give whole running text, but now you also put a separator between sentences. Even in language modeling, जैसे ऊपर हमने किया है, पूरा sentence दे रहे हैं. Next sentence में, so I live in Lahore. एक separator token आप define कर लें. Again, some fixed token, like some position token, but it's fixed. You put it in between so that the network knows that this is the end of the first sentence. And then you have another sentence. So I live in Lahore. So my area is, let's say, DHA. Okay, so this is next sentence. Then you put a SCP separated token again after that. And then you might have another token. You can put it at the start or at the end, whatever your preference. So this is another token, CLS. So what we do is we build a transformer for this whole input. Okay. And the CLS token है, which in this case is position A1, or A1 का जो भी output है Y1, Y1 would have information from all the other words in this sequence. Because of course attention हो रहा है ना, attention सारों से आ रही है, I से आ रही है, live से आ रही है, DHA से आ रही है, SAP से भी आ रही है, separator token जो है. So all of that attention is fed into this because we have attention from all places. There's no masking here. Okay? And then the output of this token is then considered to be the output of the decision whether the next sentence is the correct sentence after this sentence. So there are two sentences. So what we are trying to predict is my area is DHA, the next sentence after I live in Lahore. So of course, you have only two softmax nodes at the output layer. If it is the first sentence, the first node would be 1. And if it is second sentence, the second, I mean, if it's not true, then maybe the first sentence would be 1. If it is true, the second sentence would be 1. Second node would be 1. Output would be 1. Of course, you can use a sigmoid as well, single node. But in practice, they use a softmax over 2 nodes. So again, you are now training this on a, you can say, a classification task. Of course, the previous one was also a classification, but now in the previous case, the classification over the entire vocabulary. Now the classification is just two values. So in the original BERT, both of these task loss are combined for the training. Okay? To train the model. And since, of course, only one token is being trained for the language modeling, the Mast token, for the next sentence prediction, the CLS token. So generally the adaptation is slower. So of course, and adaptation is slower. And for that, of course, you will need more time. But as we said before, since this is a transformer, you can run it in parallel, you can run it on efficient GPUs. So that's the positive side. But generally training or adaptation of network would be slow because we're only updating one part of the network. The CLS token network part that is so CLS as well as for the mask. Of course, the mask can be at different positions. CLS would always be at the start. So both of these losses are updated or combined and updated simultaneously. So this is also something new here. You notice that both of these tasks require the same type of data. In the first task, only some words are masked. In the second task, basically you don't mask anything but update the CLS token. So first task ke liye so you're basically feeding in a complete sequence of some fixed length because this is transformer. Fixed length aapko define karni padegi. So I could have fed in I live in Lahore. My area is DHA. So this can also be used for language modeling. I can mask based on whatever my randomness has suggested. I can mask anything. Let's say live is masked or some other word is masked. Okay? So once your network is trained, meaning that all those weights have been fixed, WQ, WK, WV in the attention mechanism, as well as all the feed forward layers, as well as the output layers, then you can use this to actually, in two ways, as I said before, to generate contextual embeddings. How? So let's say आपके पास कोई नया sentence है, so let's say so now you will feed in this whole sentence into the model, and if you want to get the embedding for live, so live की जो output है इस मॉडल की, ऑफ कोर्स दैट लाइव की आउटपुट कब किस तरह आएगी, सारी अटेंशन बाकी वर्ड से भी आ रही है. जो लाइव की जो आउटपुट आएगी, दैट इज द एम्बेडिंग फॉर लाइव. नाउ दिस एम्बेडिंग would be contextual because it's based on the previous words that you have seen. So I watched the Mast live. It's not a fixed embedding that you have trained previously. Okay? So do you get this point? This is the idea of contextual embedding. Once you have trained the model, use that model to generate embeddings. Not that embeddings are stored as vectors somewhere. They are not fixed. You use the model to generate the embeddings. And those embeddings, of course, might be different for different contexts of the words that you have in your sequence. Okay? So that is one common way of using BERT, of course, to generate contextual embeddings. The other way is to reuse the entire model for some other task, which we said last time was basically the idea of pre-training / fine-tuning. So you already have a pre-trained model. And of course, these pre-trained models are available to you on the web. So Hugging Face is a library that you can find on the web, which has all of these models or many of these models pre-trained. Let me write this Hugging So I think it's available on GitHub. So this has pre-trained models available to you, given to you. Of course, these pre-trained models are also available in multiple languages. So BERT has been trained for English, and as well as in many other languages. Of course, it's not available for Urdu yet because we don't have a large corpus for Urdu available. Okay, so we're talking about pre-training and fine-tuning. So let's say if you want to do some classification problem. Okay, so let's say sentiment classification. So just take the BERT model and chop out the output layer. Yeah, even maybe some of the hidden layers if you want to, and then fine-tune that model on the data set that you have for sentiment classification. Okay? And then of course sentiment classification इसमें किस तरह होगी? You will have some CLS token and I like the movie. So इसका जो output है CLS token, this goes through the feed forward layer, this goes through the output layer to generate the predictions, which might be, let's say, positive or negative. Okay? And you train this model on the data set that you have by reusing the already pre-trained model from the language modeling that was trained for that particular language. Okay? So this step would kind of fine-tune your BERT for this task. Okay, so I hope you understand the idea of this, of masking, as well as the idea of having this a token like CLS that captures information from the entire sequence. So actually you can use the CLS also for generating sentence embeddings. Okay? So let's say sentence embedding might be, you might want to use sentence embeddings in some other application. So how can you do this? Whatever sentence you have, let's say I teach at LUMS. So you feed this into the network, and let's say you have a CLS token at the start. The output of the CLS token from this transformer would be like an embedding for this whole sequence of words that comes after it. Okay? It's a representation for I study or I teach at LUMS. So this CLS would then become like a sentence embedding, a representation for the sentence. Of course, this representation can then be further squashed through an output layer to make a prediction, like we did for sentiment classification. So any questions? Okay. So moving on, so let's talk about some other applications, and we will see that the application, the usage of these models for these other applications is not much different. Previously, traditionally in NLP, for example, machine translation or text summarization or even paraphrase generation or paraphrase detection were base and large models are basically primarily dependent on your data set size as well as your computational power. The base model, as you see, is smaller. So if your computational power is low, then you probably use the base model. And of course, the large model is larger, so you need more computational power to process that. Beyond that, of course, let's say if you want to fine tune for your own task and your data set is not very large, then I think you should prefer the base model rather than the large model. Okay, so for example, let's say if you want to do paraphrase detection. So paraphrase detection can also be done in the same way. Let's say I have a sentence, I want to lose weight. Tell me about weight loss. So both of these are paraphrases. They have the same meaning. So paraphrase detection using a transformer or using BERT, for example, would be done in a similar way. So you will have a CLS token. क्या था sentence? So I want to lose weight, SCP. Tell me about weight loss, SCP. So same way, जो CLS token का जो output होगा, you feed it through the connected layer as well as the output layer, and then go send it through a sigmoid. If it is 1, then it means that this is a paraphrase. If it is 0, then this means that it is not a paraphrase. And you train it accordingly as well. But this CLS would have information from both sentences. Okay? So this CLS would have weightages, you can say, from the second sentence as well as first sentence. So you'll get correspondences for all the words. So you'll have correspondence for, let's say, lose and loss, for example, and also all combinations. So for example, loss and weight, for example, lose and I. So all of those combinations are captured in the CLS token. And of course, the output of that CLS token, not the input. Of course, the input is set as random or 0. Okay? And based on all that relationship, you can then make a decision whether this is a paraphrase or not. Okay, now let's talk about machine translation. So machine translation, as the name suggests, is the task of converting language or running text from one language to another language. So convert text from one to another language. Okay? So this task is considered a main or key task in NLP, and it was considered to be a difficult task till I would say 2010. I would say, or say 2005. And NLP people spent a lot of energy into devising techniques for machine translation. In the initial days, they relied upon rules. So you can say a large amount of information was coded into rules, and then those rules were used to translate one language to another language. Later on, which became more popular, we had the probabilistic language models, probabilistic machine translation. So of course, probabilistic machine translation used ideas similar to what we had studied in probabilistic language modeling. Sometimes this was also called statistical language modeling. Actually, statistical language modeling is more commonly used. So the idea here was trying to find correspondences or statistics between parallel corpus. So that's another common concept. So whenever you want to learn a language or machine translation model, you need to have parallel corpora, meaning that you need to have a sentence in one language and the same sentence in the second language. So I live in Lahore. So मैं लाहौर में रहता हूँ. So we will have pairs like this in our training data set. So this is called a parallel corpus. Any data set that has pairs of language in one, pairs of running text in one language and the same running text in the second language, that is called a parallel corpus. So machine learning approaches require that you have a parallel corpus, and statistical machine translation also requires that. Okay. Of course, in the more older days also, sometimes this is an issue in recent times as well. Whenever you're trying to get data for machine translation, there's an issue of alignment. So maybe you have a book in English and you have another book, the same book that's translated in Urdu. But whenever, as you know, when you translate any text to another text, sometimes you translate not word by word or sentence by sentence, you translate holistically. So to generate reliable parallel corpora from such, you can say, data, you'll need to do alignment. You need to make sure that the two sequences of words are aligned, meaning that the first sequence of word in English and the second sequence of words in Urdu are talking about the same thing. Okay, so alignment itself is a difficult problem, and in NLP, people have spent a lot of time in alignment as well. So we won't discuss this in more detail here, but why I brought this up was to generate this parallel corpus, you need to make sure that the two sets are aligned. They talk about the same thing. Okay, so that's important. Okay, so since about 2010, we have what is now called as Neuro language models or Neuro machine translation. Actually, I'm using language models as well. Same ideas have been used for language modeling as well. So Neuro machine translation, and more recently, these were primarily LSTM and now, of course, transformer based. Okay, so the best practically usable machine translation techniques nowadays are either LSTM or transformer based. So if you go to Google Translate, for example, at the back end is most likely using some combination of LSTM or transformer. And Google Translate has become tremendously accurate over the years for resource-rich languages like English, French, Spanish, and other languages for which lots of data is available. It is very accurate, or they even say it's human accuracy. Even humans, or the accuracy of Google Translate is equivalent to that of humans. For Urdu, of course, there is still room for growth, but I have noticed over the years, in the past 2 years, it has also improved significantly for Urdu. Okay, so that was a basic intro to a machine translation. Now let's see how this is done using neural networks, LSTM and transformers. So let's first talk about using recurrent models, LSTM, for example. So in LSTM, of course, feeds in the input sentence. So LSTM is basically used as in a encoder decoder model, meaning that you have a first LSTM 1, so this is the encoder, and then you have an LSTM 2, which is the decoder. So the sentence in the source language is fed through the LSTM1, which is the encoder. After it has seen the entire source text, it generates a representation, which we say is the encoding of that source text. Now this source encoding is then fed into the decoder. So this becomes the context for the decoder. Decoder, of course, is also an LSTM. So this now becomes the context, and based on this context, it generates the first output. ठीक है? So ऊपर जैसे मैंने लिखा था, so I live in Lahore. After I fed the entire sequence into LSTM1, I get a encoding, let's say E. So this encoding is now the input to the LSTM2. So you can think of this as the context for the second LSTM. So now this E, this context then generates the first output or first distribution over the output. So let's say Y1 for the output. We are now talking about LSTM2. Okay? And let's say based on this distribution, we sample, we talked about this a few lectures back, and we generate a word. So let's say word जो generate हुआ है, I live in Lahore, मैं लाहौर में रहता हूँ. Let's say मैं ही generate हो गया. Let's say correct word generate हो गया. ठीक है? So now at the next step, it is auto-regressive. मैं का जो embedding है वो आप feed करेंगे, and then you proceed forward to generate the next word. So मैं is now fed into it, and now we generate Y2. इसको हम sample करेंगे. So let's say इसमें कुछ और लफ्ज आ जाता है, let's say गुजरात आ जाता है, for example. And then, of course, you continue in this fashion. Of course, ये जो errors होंगे, ये errors, when you're training, would be detected. They will result in a loss, and that loss would then be fed back to the even LSTM1 through LSTM2 as well as LSTM1. So this is what is meant by end-to-end training. So we have two models. So एक model में जो error generate हो रहा है, दूसरे model तक जा रहा है. And of course, this is done through the same back propagation. कोई इसमें खास additional difficulty नहीं है. We are just moving them from one layer backward to the LSTM1. So this is the standard LSTM for, which is encoder decoder model for machine translation. So what people have added to this to improve performance was the idea of attention. And I will explain why attention is important here. I mentioned that attention mechanism, when we discussed the attention mechanism, we said that attention mechanism can also be applied to LSTM or RNN or GRU, but we did not explicitly discuss that. We discussed it in the context of transformer. But I want to explain here why attention is required. So for example, you are generating, so you have an encoding after reading the whole sentence E, and based on this, you are generating outputs for the next language. Okay? So for different languages, you need to have different attentions placed to the source language to detect or to generate the best target language. So for example, रहता occurs at the second last word in the Urdu sentence. मैं लाहौर में रहता हूँ. While रहता, if you do a literal translation, is like live. While in English, live is the second word. ठीक है. So रहता in the decoder has a greater correspondence to live in the encoder. So to generate rahta in a better way, we need to know that live occurs someplace in the encoder. So that's why we place an attention mechanism for the words in the decoder to the words in the encoder. So this is now not self-attention. Remember, self-attention था आपस में words में attention करना. This is now cross-attention. Of course, in a transformer वो आप easily manage कर सकते. जैसे हमने 2 sentences डाले, बीच में शब्द निकाला, तो सारा वो attention उसमें आ गया. But here, of course, you have an encoder, you have a decoder, so you can think of this as not self-attention, but cross-attention. So you can build a cross-attention model to keep track of which word from the source helps predict the target. Okay. So people have done LSTM encoder decoder with attention for machine translation as well. And those typically give better results. Okay. So let me now quickly discuss an evaluation measure. I want to actually complete some basic things today. I think we discussed a few weeks back that whatever we covered till today would be part of the exam. What we cover next week would not be part of the exam. So that's why I'm covering some things that are essential and should be tested in the exam. Okay, so how do you evaluate the performance of machine translation? Of course, you can have human evaluation, which of course is costly, but it is also the best. Okay? But we need to have some other automatic way of evaluation as well. Okay? So automatic evaluation में कुछ measures available हैं. Of course, there are some measures that are more recent. वो probably हम discuss नहीं करेंगे. We'll talk about the one that is most popular and has been used for, let's say, a few decades. And that is called BLEU. So this is called bilingual evaluation under study. So it's kind of a difficult name, but it's basically called a blue score. So BLEU score. So blue score quantifies in an automatic way the quality of your machine translation. And what do you have as, how do you judge your quality? So for example, I live, okay. So you want to generate some output. So you have some references, meaning that the true desired translations or outputs. So there could be multiple of them, not one. Remember, language can be written in multiple ways. So I live in Lahore. So this is maybe one correct output. Another output is, I don't know, इसकी कोई variation क्या बनेगी? For example, he lives in Lahore, although this is not entirely correct, but maybe this is also a correct reference translation. Okay? And there might be others as well. So there might be others. So these are reference sentences, and then there is also the generated sentence. So generated might be erroneous. For example, live I Lahore, for example. Okay. So now we want to determine how correct is this generated sentence given some references that we have. So references could be one or more. So references are correct generations or translation. By the way, this approach is used wherever you have language generation. So you can also use it for paraphrase generation. You can also use it for summarization. Although for summarization, there is another measure called Rouge, which we'll also talk about. Very similar to this, by the way. But here we're actually talking about the blue score. Okay? So the blue score is actually a precision-based measure. Okay? So let's see, and of course there are some modifications. So let me take examples that are more common. Okay, let me take this sentence. So let's say this is my generated output और references मेरे पास ये हैं cat sat on mat, the cat sat on the mat. So there is a cat on the mat, for example. So there could be various reference sentences. Okay. हमारी generated sentence the और cat है. A precision is what? So precision is based on the generated sentence. So there are only two words that are generated, the and cat. So does the occur in the reference? Yes, it does. Does cat occurs in the reference? Yes, it does. How many total words are there in the generated? Two. Both of them do occur in the reference. So it means that 2/2. Okay. So the precision is 1. Okay. So that is how precision is computed. But as I said, blue score has some variations. So let me take another example. Let's say D. Let's say ये मेरी generated output है. According to my previous approach, D 4 दफा आया है. So हर एक word D, is it present in the reference? Yes, it is present. D को मैंने देखा, D नजर आ रहा है. दूसरे D को देखा, वो भी नजर आ रहा है. तीसरे को देखा, वो भी नजर आता है. Again, 4/4 is equal to 1. But of course, this is a poorer sentence. So how do you handle this? They clip the precision, and they call this the clipped or modified precision. So how do they clip it? If there is a word that's repeated multiple times in the generated text, we only count it to the extent that it is repeated in the references. So D जो है वो references में maximum 2 दफा एक reference में आ रहा है. So the cat sat on the mat. 2 दफा D आ रहा है. ठीक है? So in that sense, we will only count D twice. We will not count 4 times. So this would give us then 204.5. So maximum D for any particular word, जितनी दफा भी आ रहा है उतनी दफा ही हम काउंट करेंगे generated sentence में. उसको उससे ज़्यादा नहीं करेंगे. ठीक है? And of course, generated sentence has 4 words, so 2/4 would give you the precision. ठीक है? So okay, so this is the idea of the clipped or modified precision. But so far we have only used unigrams. So blue can also use higher order n-grams. ठीक है? So generally the blue unigram is called blue 1. And if you are using bigrams, we call it blue 2. And usually we typically go up to blue 4. So what does Bluetooth means? For example, मेरा generated sentence the cat था. So there is only one bigram, which is the cat. The sequence the cat. Is the cat occurring in my reference? Yes, it is. ठीक है, so the cat does occur in the references. ठीक है. So which means that there is only one bigram in the generated test, so 1/1 is 1. Okay? But if you have a longer sentence, so for example, the cat met the. So इसमें bigrams क्या है हमारे पास? The cat है एक, तो उसके बाद है cat met है and met the है. So 3 bigrams. Now you check, do all these 3 occur in my references? The cat तो आता है, cat mat नहीं आ रहा, cat sat on the mat. There is a cat on the mat, no. Mat the. Let me just paste it. वो क्या था? There is a cat on the mat. Mat D तो कोई नहीं है ना. ठीक है. So basically this is going to be 1/3. ठीक है. So 3 generated bigrams हैं, उसमें से सिर्फ एक आ रहा है आपका references में. ठीक है. And of course you can extend this to trigrams, and for higher end we typically go to 4 grams. Okay, and 4 grams people have said that it kind of corresponds more closely to what humans look at when they are looking at translations. But you can use any one of these as well. 2 grams is also fine for many applications. Okay, but that is not all in Blue Score. So Blue Score has 2 other things. One is the issue of the generated sentence being very small. So let's say आपके पास बहुत small generated sentence, सिर्फ cat generate हुआ है. So whenever your generated sentence is small, obviously precision would be high because denominator में 1 आएगा या 2 आएगा, वो थोड़ा number आएगा. So we want to penalize shorter generated sentences or text. So we call that the brevity penalty. Okay? And the brevity penalty is a penalty that is multiplied with the blue score that we have seen so far, the modified or the clipped blue score. It could be blue 1, blue 2, blue 3, blue 4, and so on. Sometimes we also take the averages of these. Blue 2, blue 3, blue 4 का average भी ले लेते हैं sometimes. So how do you compute this brevity? So we have a formula EXP. EXP is the E, which is 2.7 something. 1 minus reference over R over G. So EXP is basically the exponent. So इसको मैं किसी और तरीके से लिखूँ तो this is E exponent 1 minus R divided by G. ठीक है? So what is R? So R is the length of the reference sentence closest to the okay, and G of course is the length of the generated sentence. Okay, so हमारा जो था ऊपर, द कैट सैट ऑन द मैट, तो ये कितना है, 5 है. देयर इज ए कैट ऑन द मैट, दिस इज 6. ठीक है. कैट सैट ऑन मैट, तो दिस इज 3. ठीक है. 4 होगा. ये 6 है शायद, I don't know. Anyway, you understand the idea. So for each sentence, generated sentence, we choose that reference sentence that is closest in length to the generated sentence. So let's say मेरे पास एक छोटा sentence मैंने generate किया, the cat, which is 2. ठीक है. So g is equal to 2. इसका जो reference हम use करेंगे वो 4 वाला use करेंगे, because that is closest to 2. ठीक है. And then of course exp 1 minus r is reference is 4 divided by 2. जो भी ये वैल्यू आएगी इसको आपने उससे मल्टीप्लाई कर देना, जो भी आपका ब्लू स्कोर है. So by the way, r and c, if they are same length, exponent r over c 1 हो, r over g by the way is 1 हो जाएगा. 1 minus 1 is 0. Anything raised to power of 0 is 1. So there is no brevity penalty. ठीक है. But let's say if r, which is a reference, or let's say if g is small and reference is large, so ऊपर ये जो रेशियो है ये नेगेटिव में आएगी, एक्सपोनेंट नेगेटिव होगा. ठीक है. So which means that you are not dividing the answer that you get will be less than 1. Okay. So you are reducing the blue score because the generated text was small. Okay. And of course, by the way, you don't apply this brevity penalty if R is greater than G. What happened here? Okay. So this is only applied when G is less than R. Okay. It is not applied when G is equal. Of course, equal होगा तो 0 हो जाएगा और 1 आ जाएगा answer, doesn't make any difference, and not applied when G is greater than R. Okay, one final thing. So far we have talked about one sentence, but whenever you are evaluating, you evaluate over multiple sentences or a large corpus. So how do you combine values from multiple sentences? You can take the arithmetic mean, but what is more commonly recommended is the geometric mean. So geometric mean क्या चीज होती है? So let's say आपके पास 4 sentences हैं. Is my text visible?
No, sir.
I don't know. Let's see. Okay, let me just, I think it has hanged up or something. So is it visible now, text typing?
Yes, sir.
Okay, so we're also running out of time. All right. So basically what I was mentioning was that if you have multiple sentences, you can take the geometric mean. So for example, let's say you have blue score for sentence 1 and you have blue score for sentence 2. The geometric mean would be what? So B into S1 multiplied by B into S2 raised to power of 1/2. I think it's hanged up again. What's happening? I don't know, there's some issue with the system right now. So, okay, I think probably I'll stop here. We are running out of time as well. Any questions? Any questions? No questions?
Sir, next week will be the last week.
जी
Next
आवाज नहीं
week will be the
मुझे आवाज नहीं आ रही आपकी एनी कमेंट फीडबैक आपकी वैसे समझ नहीं आई कोई बोला तो था बट आई डिडंट गेट इट जी, next week will be the last week. So we will be covering new material next week, but we will decide कि उसमें कुछ हमने include करना है कि नहीं करना है final में. Okay. So next 2 weeks के दोनों lectures में I think I will be covering new material because we still have few things to be discussed.
एंड सर एग्जाम फाइनल एग्जाम किस वीक में होगा?
फाइनल एग्जाम का मेरे ख्याल से टाइम आपको बताया हुआ है. आई थिंक आइदर अराउंड May 10 या May 2 या 3 बिकॉज दोनों कोर्सेज के इन दोनों में से मुझे नहीं पता आपका NLP का या डेटा माइनिंग का कब है, बट इन 2 डेज के लगभग है. गो चेक ऑन जम्बील, वही फिक्स डेट वही होगी, कोई उसमें चेंज नहीं होगी. जो आपका अनाउंस डेट है वही होगी, डेट एंड टाइम. Okay, anything else? चले फिर. I think with that I think we can conclude for today.